Internet-scale pre-training has given neural networks the ability to recognize objects and follow complex instructions. Now we are asking them to apply those insights to physical movement in a fraction of a second. Vision language models can identify targets and understand spatial constraints, but this high-level reasoning is often detached from the physics of motion. Generating a logical plan is relatively straightforward. Generating the exact sequence of continuous motor torques needed to execute that plan is the primary bottleneck in modern robotics. This creates a modality gap. Pre-trained VLMs natively output language as discrete text tokens, but physical robots require continuous, high-dimensional joint commands. To prevent failure, these commands must flow into the motors at 50 Hz or faster. To bridge this gap, engineers use a Vision Language Action, or VLA, policy. Mathematically formulated as pi theta, this framework takes three inputs: the visual observation O, the language instruction L, and the robot's proprioceptive state Q. The network must fuse these distinct inputs to output A, the continuous physical action space. Resolving the engineering tension between generating semantic text tokens and providing continuous physical control is the central challenge for deploying generalized embodied AI. Over 180 distinct VLA architectures have been proposed recently to solve this exact translation problem. To evaluate which system actually works, we can map the entire ecosystem into a strict structural taxonomy. The field is currently split into four competing architectural families: autoregressive, flow-based, diffusion, and hybrid. These four approaches are being evaluated against the most physically demanding scenarios: tightly coupled bimanual arm coordination and under-actuated drone flight. The choice of action head architecture ultimately dictates the physical reflexes, computational latency, and hardware capabilities of the final system. The autoregressive approach, utilized by models like RT2 and OpenVLA, treats physical actions as a sequence of language predictions. This architecture leverages the native sequence generation of the language model backbone. It takes the continuous joint data required to move an arm and slices it into discrete bins per dimension, processing motor torques as if they were vocabulary words. This introduces quantization artifacts. Slicing a continuous motion into predefined bins can strip away the micro-precision required for delicate, contact-rich tasks like threading a needle or grasping a fragile object. It also creates sequential latency. To move a standard bimanual setup requires a 16-dimensional action space. Predicting a 16-variable matrix token by token creates compounding delays that stack up with every motor adjustment. Autoregressive models utilize the extensive weights of pre-trained language models, but their discrete nature can limit high-frequency physical agility. Diffusion VLAs, such as RDT1B, avoid tokenization by treating physical movement as a continuous generative denoising process. In this pipeline, the action head generates trajectories using the same mechanics as a diffusion-based image generator. Diffusion models excel at mapping out multiple valid action distributions simultaneously. If asked to pick up a cup, the network models both a left-handed and right-handed grasp before collapsing into a single final decision. Relying on a reverse diffusion process, the network denoises a sample of Gaussian noise over 50 to 100 steps, resolving the static into a fluid trajectory. But these cycles push inference latency to roughly 300 milliseconds per action chunk. A 300 millisecond delay inside a 50 Hz control loop makes real-time control difficult. Without aggressive distillation, pure diffusion architectures are currently too slow for agile hardware. Flow-matching architectures like Pi0 attempt to bridge this gap. They retain the continuous generation of diffusion, but aim to reduce the latency. The flow-based action head is driven by a distinct mathematical formulation. Instead of taking a stochastic random walk to denoise a sample, flow matching regresses a direct vector field. It calculates a path that transports samples from a Gaussian prior directly to the target action distribution. Because this path is more direct, the vector field requires as few as 10 steps to generate a continuous 16-dimensional action chunk. This combines the trajectory smoothness of a generative policy with an inference speed fast enough to hit 50 Hz control loops. We can track how these mathematical differences translate to hardware by looking at standardized simulation benchmarks. This table compares success rates across standard evaluation suites. On the Libero long tasks requiring complex navigation, The flow-based Pi0 scores 78.4, while the autoregressive OpenVLA reaches just 53.7. This performance gap suggests that coherent, continuous generation is a significant factor for long-horizon physical stability. Some researchers have moved toward hybrid architectures, which route binary gripper commands to an autoregressive head and smooth joint motions to a flow-based head. While the field continues to evolve, the current data shows flow-matching architectures setting the high watermark for tasks requiring stable, continuous interaction. Generating a fast, precise action is only useful if the system can keep up with the robot's physical movement. To bypass the latency of the VLM, modern models use action chunking. Instead of single motor movements, the policy predicts a sequence of future actions simultaneously. A typical chunk contains 50 time steps across 16 dimensions, outputting an 800-variable matrix of future states. The robot executes this sequence either open-loop or by averaging overlapping chunks. This amortizes the heady computational weight of the neural network over 50 physical control steps. Action chunking provides a temporal buffer. It ensures the motors have immediate instructions, while the massive AI models process observations in the background. The action chunking matrix is indifferent to the physical machine it controls. On the left, this matrix maps cleanly to a bimanual setup, driving two arms to coordinate complex timing. On the right, a drone's rotors and spatial attitude create an identically coupled matrix. The same language processing that allows a model to understand "fold the shirt neatly" can be used for commands like "fly to the red building and inspect the roof," following the same generation path to execute the command. This cross-domain capability suggests that the primary challenges of bimanual coordination and aerial control are converging. The same VLA stack that manages the precision of a robotic arm is now proving capable of stabilizing a drone's flight path.